So yeah, let me throw over our Canvas course here, and I'll go to look at it as a student here. Okay, so let's see how we're going to proceed with this. But under the tolerancing worksheets, all I've what I've just talked through on the board is the making a case for it. In that that drawing just shows that size on size doesn't work, and that a great way to explore this is through the hole and shaft relationship that we experience a lot in mechanical world. It's a real common fit. Even if it's just a bolt in a hole, that is still kind of like a shaft in a hole. And we use fasteners all the time in the mechanical world. So that kind of relationship is captured in a hole and a shaft type of a relationship. So there's my PDF and my drawing for that. And then, so these are our resources that we'll need here. And so this comes out of this. So I'll open up this tolerancing AutoCAD textbook. Technically, that's where this is just clipped out of an actual textbook that I could hand you, but we only need a few chapters this week and next for some other stuff. So I think I already have mine up here. But if I open that document, it's this one. It's like a 38-page PDF. It was chapter 4 of that version. I think it's later in my book. It's kind of in the advanced techniques of my book, actually, from 2023 AutoCAD. But I mean, this is good reading. I'm not going to sit here and go through all of this, but like, because I've summed up mine Cliff Notes version of that. Yep, my little pictures in my case studies kind of show what I'm getting at here. At least case study 1 and 2 that we're going to try to with tolerancing get up to 70% of parts fitting here together. So this is good reading and understanding, though. This is all kind of it goes through a little bit of how those tolerances can be displayed, limit dimensions, plus minus tolerances, page or block tolerances. We're kind of using both. It's going to talk through that relationship of a shaft going into a hole. It's gonna bring out some terminology that we probably already have learned a little bit. I can't remember which chapters for sure, and there'll be some more that we talk about. But these terms we'll explore definitely the limits, the basic size, tolerance, MMC, which is maximum material condition, and LMC, which is least material condition. So I'll talk a little bit more in depth about those, but these are some terms that you may have come across in your theory studies already, and we're gonna kind of put them to work here, maybe help make. I know when you're reading some of that in theory, unless you're actually doing something that's talking about it, maybe don't doesn't stick with you as well. So we'll try to put some of these words to use here. The one I'm going to point out first here is this basic size. So basic size. The basic size is the size from which the limits are calculated. So it's common for both the hole and the shaft, and is usually the value of the closest fraction. So I say basic size is also kind of maybe in my mind I collude it with nominal size, and that just means like it may not be the true size, but it's maybe a size where we're basing it's kind of a basis point and then if I understand the tolerances I actually get the actual size, so it's definitely different from an actual size or a measured size. A basic size can be kind of like this foundation where we're going to plan from, and yeah, so that's a good term to understand, and I definitely, yeah, confuse the two a little bit, and you'll probably hear me say nominal and basic size a little bit interchangeably. Whether or not I should do that, my mind just hasn't quite sorted that out, so I sometimes will say it wrong or whatever. But as a quick note for CAD, basic sizes are dimension with a rectangular box around them. And so we can actually set a dimension. In fact, if you pulled up the ISU inch template and you like looked through the dimension styles, there probably is a basic, there might be one that's labeled basic dimension or something. And that means it's going to put a rectangular little box around your dimension. And that's, if you see those on prints, that's called a basic size, a nominal size, and not an actual size. But it might be a size that I'm working from. So, and then we'll go into the weeds a little bit about MMC and LMC in just a little bit here. We'll wait till we maybe look at it on a print. I'm perusing through this just so you know that this is where this is a good chapter to be familiar with in order to do these worksheets. You don't have to read the whole thing, but maybe just be familiar with it. Because what it goes through is the types of fits we can have here. So I don't know, I'm only like 5 pages in, and they start to talk about types of fits. And I kind of mentioned that there's different ways we can have that hole and shaft relationship. We can have clearance fits, interference fits, a transition fit, a line fit. So these are kinds of fits, and we'll come back and use what I've clipped out this little in our assignment sheets. I've clipped out this little box. It's kind of an important one on 4.5. I think on our assignment sheets I actually reference like maybe the page number from these. So we'll come back to this one. Let me peruse through a little bit more. We've got some definitions of those fits, and we've got their abbreviations here. So you'll start to see hieroglyphics. We like shorthand notation. So RC, LC, LT, LN. These are all just abbreviations for these types of fits, which I understand. All I'm doing is just planting some seeds. This still may be confusing to you, but there is a little bit of definition going on here in this document about what those are. Okay, so I'm going to come down. Oh, and here's I actually like this one pretty well, where it does break down these the abbreviations with maybe their actual description and then how they're used in design here. So sometimes we as drafters don't understand this as well. Engineers will have to understand this maybe a little bit better, or maybe it'll be previous part design that's proved that hey, we're using, this is an RC1 fit, and you'd be like, I don't know what that is. I do remember seeing that in class, but it looks like at this company that I'm working for, they're using some of this terminology that I've kind of learned. Yeah, you'll see this show up at places and maybe sometimes not. And then where people aren't considering these kind of fits, they're having probably problems with things fitting right. So the reality is our engineering world has already kind of has really categorized how things fit. And as long as we understand or we have the reference material to try to understand like how our part is going to function, there's probably a fit that's been engineered to make it function uh, best as long as we know where that reference material is and we can identify our type of fit. So the work has been done. The engineered work has kind of been done as long as we can identify where we fit into it. Okay, so and there's FN fits. Okay, good. They have some maybe a little more complicated assemblies that are showing where some of this might. I don't know what this particular part is, a milling jack assembly tolerances, but here's some parts that have to fit together specifically. So in this case, there's probably an application for some of these types of fits to be detailed correctly. And I don't know how in the weeds they go about some of these, but they're talking about, oh, okay, those individual parts and maybe some of the tolerancing applied to them. Okay, I don't know. But we have they attend to metric tolerances as well. So we've got there's going to be reference tables for both inch type dimensions and metric dimensions, which is pretty standard. So I'm down here on page like 15 of my document, and these ones you'll see too. Here's some more fit symbols and what they are and their description. So there's just these other different categorized. Maybe I'm in the metric categories here now, ANSI standard limits and fits. I just want to point out just the look of these, how they shorthand notate this, like an H11 slash C11, a C11 slash H11. Down here, I don't know, H7 slash H6. I point these out because some 3D programs, Inventor, when we get to it, will already have these fits already built in to be able to apply pretty quick. And they're gonna and so some of these codes you're gonna see show up in some 3D programs that are already going to be, pre-programmed in Inventor to apply that engineered design. And so I just wanted to point out these little this little notation here, which makes zero sense to us right now until we start exploring it. But pointing that out. Okay, let me see. Basic hull shaft system. So there's more information down here eventually, and then they have some more descriptions. Okay. Tolerance accumulation. Okay. A lot of information here. It's good. Even some crossword puzzles if you're really that bored. These would be great. I'm not going to make you do the crossword puzzles. I should make you do the crossword puzzles, but down here is where, so at the very end of this, like the last, I think when I'm down here in page like 27 to 38, this is where these are kind of what we're going to fill out, or we're going to fill out these worksheets. I've just made them in a Word document so they're easier just to work from your computer and type in the dimensions here. But so I've got this document here, this document. So all I've done is extract these and I think, yeah, essentially I've extracted the critical documents down here to actually try to research and figure out how what the tolerances should be for some different fits is what we're going to look at. So the next thing I have in the tolerancing worksheet assignment, that is this tolerancing AutoCAD textbook we just went through right here. You don't totally need it. It's just extra reading and it does show you where everything came from. And there are some on the worksheets, it does point back to that document if you want some further reading or to understand maybe these worksheets will say, oh, go look at like page 4-25 or whatever from that document. And it may have some of the definitions to help better understand what we're doing here. So this is a good resource. And then the one we absolutely have to have is this Appendix A, and this is just out of the same it's out of the AutoCAD book. They just had to apply they just had to put in some reference material for us to work with. So this is something that could exist. In your company, they may have pulled out some reference work that they've used for years, and it's in some file in a library where they have some reference documentation. And that's what this part is here, Appendix A, limits and fits. It's from the same AutoCAD book, but it's probably clipped out of some other. I'm sure they borrowed it from some other source actually, because these are legit tolerances. But so you need to have Appendix A. So I'm going to scroll through this a little bit just to get familiar. It's a 12-page document. This is where we're going to pull most of our dimensions from on some of the worksheets, not all the worksheets, but some of them, because these are the limits and fits appendix. And so what I have to know is some of the problems are going to say, hey, this is the fit. It's designated with that shorthand notation, and you'll look for that notation here. So this first page looks like it's running or sliding clearance fits, which would be RC designated fits, RC 1, 2, 3, and 4. So I'm looking at the columns here. These are the kinds of fits, RC 1, 2, 3, and 4. Then over here, this is a nominal size, or I could even say basic size. Probably why I get it confused is they even call this leftmost column nominal sizes. So these are nominal like hole and shaft sizes, what we're going to be applying this to. But so these are actually dimensions. Like these are, I mean, that's a 0 to 0.12, less than an eighth of an inch hole and like shaft size. So pretty small. And they go all the way up to 15 to almost 20 inch. These are in inch units, by the way. 15 or almost 19 point something inches of shaft and hole size. So this chart covers quite a bit of ground with RC class fits. So let me go to the next page. This is kind of, yeah, go ahead. We're kind of learning. We're just barely starting learning that now. In your theory textbook, it might be talking about those this week if you're looking through some of your questions. So the stuff I'm talking about, you're probably going to read about a little bit in theory. And yeah. And I don't think you're gonna, and don't try to like, I always tell everybody with their theory book, don't try to think you can memorize it all. Just, it's planting some seeds of like reading and learning some of the terminology and hope things will start to click. But I give yourself like 5 years and actually working in an environment where they're applying this kind of, yeah, you may not end up in an environment where I'm never looking up class of fits, or it doesn't seem to be something the engineers are telling me to worry about. And that might be the case where you work. So this is just yeah, this is kind of a situation of a highly controlled uh, environment where we are really concerned about how parts are fitting together. And yeah, yeah. Yeah, exactly right. Yeah, usually it's going to be because we're not engineers and we might be new drafters. It might be like, I don't really understand, but hopefully an engineer or hopefully the company has some standards they've established to be like, hey, these are the kind of fits we need for this particular part. This is the kind of fit it will need. And for this particular part, it might be this different kind of fit. So yeah, it's this like broad spectrum learning on what are these shaft and hole relationships that can, and it's a pretty deep dive, and we're only probably looking at, I mean, my chart here already captures what, I don't know, quite a few different shaft sizes, but one, two, three, four different types of fits right here that are just running and sliding clearance fits, and we've got about 12 pages of documents so I mean, we're probably looking at a couple hundred different types of fit relationships that could exist just in our simple appendix. So what I mean is it's a pretty deep study, and it really goes back to the engineered design intent. And what we need to be able to understand is like, is there a reference sheet somewhere that I can help remember? And you're never going to memorize any of this, right? It's just like if I ever see this in the industry, or if I'm using a program like Inventor and I see that I could apply this like weird coded looking class of fit, I would know like, hey, that is like a tolerance class of fit that I'm looking at because I can recognize the acronym or I can recognize kind of what I call the hieroglyphics. I can be like, oh, that I remember that. That's like tolerance specific dimensioning. And so you'll see this pop up in the program when you're poking through it in your life. And I'll point it out I mean, we'll use this when we go to Inventor and we can even and in our case in AutoCAD, we can establish a dimension style to capture these class of fits. They're not preloaded or programmed into it, but if one of these was really important that I use all the time, I could build a dimension style to capture it. And so this is why in a real template and in a really controlled, highly critical drafting area, uh, when you click on your dimension styles in those templates, they might have 20 or 30 different dimension styles built for 20 or 30 different class of fits or other situations they're routinely using in their design and their product. Yeah, I guess that's what I mean. It's like a deep dive here. It's like it's a sleeper session, but it's really important. I actually really like this stuff. This is what makes me a mechanical drafter is I don't mind digging through information and trying to get things right. I'm especially interested in it when we've had routine part failures, and really it's just because we're not paying attention to like the relationship of parts, and that is sometimes causing part failures, and that still happens in every company every day, all day long, fixing problems to solutions. And sometimes it's just a matter of we are not applying like already it's almost like there's these predetermined engineered designs that exist. We just need to implement them maybe in our practice to prevent future failures. So I love that kind of stuff. And so it gets me digging in the weeds of reference data like this because all you're looking for is something that's probably already been figured out in the past and documented somewhere. That's essentially what we're looking at. Past failures have caused people to assemble this kind of information. What I want to point out about these tables, though, is you got to kind of read them kind of carefully here. So I'm still on this table one, but they all are kind of similar. This is a basic hole system. Limits are in thousandths of an inch. So when they're showing you here, when you're looking at these numbers in these class of fit columns here, and one is designated, like one of these columns is designated for a hole and one is designated for a shaft. What you're looking at is these are the tolerances that apply to those situations, and these are in thousandths of an inch. So if I see zero, that means like 0 thousandths. If I see a one in a category, that's like 1 thousandth. So this is like 1.4 thousandths. So that would look like 0.0014. It's like if I think of that right, yeah, 001 is 1 thousandths, and then four, I would move the decimal place. So that dimension, like if I'm looking at this one right here, this minus 1.4, that looks like on paper different than you're thinking here. So remember, these are in, and it says right here, these are in thousandths. The limits are in thousandths of an inch. So this is another thing that's hard for people to understand that is actually 1 thousandths here, this 1.0. So decimally, that looks like 0.001. That's 1 thousandth. So this is kind of shorthand notation. Machinists are really used to looking at thousandths of an inch, like in this shorthand notation. It's almost like they just moved the decimal place over a few times. This confuses the heck out of students, though. So I'll help you walk through this a little bit. That chart is in thousandths of an inch tolerances. Because if it was a 1 inch diameter, or this is almost like in this column, I'm looking at this row right here, 1.97 to 3.15. That's the hole or shaft size. That wouldn't make sense for this to be able to be 1.8 inches over that. Not at all. So these are thousandths of an inch. That's 0.0018 that it could be over for this type of fit on the hole size. Next page, let's look at it. I'm not going to go into detail on all these pages. I just wanted to like kind of nerd out on one. So RC2, 3, 4, different maybe diameters. I don't know. Let's look. The next one is same RC6, 7, 8, 9. So it looks like there's RC1 through 9 types of fits for running and sliding fits. Is that what it is? Yeah, running or sliding clearance fits. Okay, let's go down to the next one. Oh, locational clearance fit. So they kind of have an LC prefix, I guess. LC 1, 2, 3, 4, 5, 6, 7, 8. Similar charting, still in thousandths of an inch, just a different type of fit. It's a different relationship between the hole and shaft. Okay. And a whole bunch of those. Then we've got still going on LC 9, 10, and 11. So out to LC 1 to LC 11 for locational clearance, I think is what they were called. Yep. Locational clearance fits. Totally different fit from the RC fits. Okay. And then an LT fit, we've got these locational transition fits. Still a chart in thousandths of an inch, still in inches. And so it looks like we have an LT 1, 2, 3, 4, 5, 6. So there is a systematic code to this, is what it's also. That's all. It looks like it's else. At least we're only capturing on our reference material. If it's an LT type fit, we only got 1 through 6 designated. On the next page, what is it? Locational interference. So that's an LN fit. LN 1, 2, 3. What's that? Location what? Oh yeah. Yeah, these are just refer. I'm just digging through this like document because you're gonna need to dig through. You're gonna be digging through this document pretty heavily here in just a minute. Oh, one of my pages I'm missing? Oh, it's like because you're looking at my page numbers or what? A6. Maybe we haven't got to him yet. I don't know. I'm not missing any pages for sure. I'm looking at my page numbers here. So yeah, A5, A6. I'm not saying they're capturing every type of fit. They've provided us some because now we're into force and shrink fits. Locational interference, LN. We have FN. LT, what? There's LT, right? You guys don't have it in yours? Is that what you're saying? Your document does not have it? What the freak? That's what you're saying. Now I'm on board. I'm thinking you already know which fit we're missing and wherever. Okay, okay. So my document that I've uploaded does not have this? What the heck? That's impossible. No, I don't know. It should be the same document, this one here, right? Because I'm open mind for my drive, but yeah, I'll just scroll through. Maybe I got to re-upload it. 3, 4, 5, right there, huh? And then 6. Oh, let me re-upload. Good point. I don't know why this didn't come through. So, oh, it's definitely important. Everybody has a blank one. That's funny because it should be that same document. Let me leave this. Let me address that right now because you got to have that. The funny thing is that's the same. It's almost like it just didn't like for whatever reason it didn't come through right. So let me edit this out. Let me delete that one and I'll bring in another one. It might say it's a copy if I don't, but that's okay. I'm going to bring it in. Because I think I only have one version of this. It's kind of funny that pretty sure the version I loaded has the same name. So I have seen this happen though a little bit. Oh, weird. So you're getting like half of it coming through. Maybe, and so I'm going to load this and I'm going to save it, and then we'll see if it'll have -1 because I should have a document already exists in there, but yeah, like I said, it's like not coming through. So if I save here and then you give it a few seconds and you guys do like a refresh on your browser maybe, and then you re-download that one maybe, and I don't know if it's different like previewing it in the window. Like it would be okay to download here too. Like you have it now. Cool, good. I'm glad. Hey, thanks for pointing that out. I wouldn't have known that. And yeah, likely there's a few questions from that page too. I can't say we use every page in this document, but I'm with you now. You don't have it. Yeah. Sweet. Yeah. And I don't know if sometimes the preview window cuts stuff off. If you download it, maybe it shows up, but not so. I have done that to myself and I've been like, why does that page disappear? And so I just think sometimes these PDFs become corrupt. So now you should have it. Yes. And I'm going to scroll down through here. I mean, it bugs me that's all crooked. I have new copies to scan in so they're straight. So Yeah, the numbers are clear. I agree with that. So I was able to work from it last year a little bit. So it didn't. Yeah, I do have a new set to scan in though at some point. But so shaft basis. Oh yeah. So what are we in? I just want to go up a little bit. It transitions to metric, I think, at about page 6 or 7. So now we start to see metric limits and fits. And so what we see is that other coding is that I mean they categorize their tables just a little bit different. They still have kind of a basic size, which would be in millimeters now. And then we have kind of the loose running, free running, close running, sliding, locational clearance. And then they have that subcode here. This is what shows up in Inventor for sure, is where I see these H11, C11, H9, D9. It's like capital letters for the whole, and the smaller lowercase letters are generally shaft. And so just watch for that. I mean, there's a systematic coding that they've used here too. Yes. What's interesting to me is I worked for a company where we finally started to apply some of this, some of these fits, and it was because we just were getting people that weren't considering uh, just the class of fit that we needed for the application, and we had stuff. And what it's detrimental to the hole and size because it can wear things out too soon. It can also be undersized and have breakage occur, like the shaft could break if there's too much slop or wear on this thing. And so we were having some breakage is what we were having, and we were having some undersized shaft, and we would buy bearings that would fit, and bearings will come designated by how the shaft needs to fit in a bearing, and it's really specific that the shaft fits a bearing exactly right. And you have bearings all over in your car, and you have bearings all over in a lot of stuff that you'd probably take for granted, but the way things insert into bearings are very critical. And so and that's just I mean, almost every mechanical part out there has a bearing associated with it or a shaft into a hole. So we just found that we weren't holding critical enough tolerances. And it was causing random breakage, which is the worst. It took them a while to pattern, like, why are we breaking here and here and here? It's like we built this stuff for 100 years. What's going on? Well, we're just getting sloppy with our tolerances and we weren't tolerancing things correct. So it was a whole rein in scenario that I lived through. And all we had to do is really just apply what's already been done. Just apply the standards that have been built. So shaft and base. So we're still into millimeter charts. So I think the millimeters take us out to the end when we have some metric designations here. So all right. So now let's look at a worksheet and just work from it as drafters, as if we don't really know the design intent, but we know we're given some information. We need to go through some charts and pull out some so that I can build my dimensions on a print. That's what I need to know as a drafter. I've got some charting. They're going to give me some fits. They're going to give me some sizes, some basic sizes, and some fit design intent. I'm going to need to go through these charts and determine how to build my dimension style. It's kind of what I'm doing this for. So I'm the one in charge of dimensioning prints as a drafter. So I got to know how to build tolerance dimensions. So yeah, here we go. So yeah, go ahead. Yes, I will. As soon as I get over here. Yeah. Yep, we can. Exactly. Good, good, good. I think I'm back. I'm back. Yeah, so let's see. opening worksheet number 1 now. So let's put some of this reference stuff to work here. So let's look at worksheet 1, which is this one. So it starts with an example and then some information. So usually the first 2 sheets on these, or at least the first sheet on every one of these, is just one worked through example, and then maybe some and then below it, for each little thing that I had to figure out about this, there's a brief explanation on where maybe that information came from. So when I'm looking at these tolerance sheets, this is actually the problem sets that we're going to work on here. So what we have is like a shaft and hole limits, and really I have like I can do A, B, C, D, E, F, G, and H. We don't have to do all of these, but I potentially these are all problems A through H, and they kind of give us like a shaft and a hole relationship that's going on here. So what we're looking at is kind of columns down as individual problems. So this particular example has been taken from column A, and the shaft and hole and kind of how they're going to work together. And maybe I'm going to identify the type of fit once I know what the clearance is essentially on these. So these are a little bit different. I don't think I really have to reference the appendix on these ones yet. I can actually just look at the numbers and do some solving myself. And then I could develop a dimension style that went with this if I needed to. So we'll walk through this one in just a second, but let me just explain how these worksheets look like. So yeah, there's a whole problem set here. There's an example problem that's been solved, and there's some definitions for each one of these columns here of what we're looking for. Looks like it takes up the first couple sheets on this one. And then you scroll down, and these will be the ones we actually need to solve. So all we really have to solve here are B, C, and D. I don't have to do E, F, G, and H. Those are future assignments potentially. So just more of the same. So we're just doing 3 different sets. So let's go look at A. This is a pretty common format for these worksheets, though. They'll be the first part shows all the problems that are possible with one of them that's been worked out with maybe some explanations of those individual rows right here and maybe where they were found. I think some of this on some of these it'll point back to that the textbook PDF that we weren't missing the page on the textbook. We were missing the page on the appendix, but you might, I don't see any here. Oh yeah, right here. So when it said, when you see something like definitions are on page 4.5, table 4.1, this is going back to that the textbook, the tolerancing textbook. That's the 38-page document. So it's going to be talking back to this particular document and the page number associated with maybe some explanation of what the heck that kind of fit is. So just so you're aware of how this is kind of laid out for an assignment. It's a bit confusing for sure. And I've tried to simplify a little bit more because it was even more confusing before. And there was no way to fill it out. I had to just build it so you could actually do it on the computer unless you want to do them by hand. And I don't want to read them by hand. So I'd rather I'm done on the computer. Easier to share. So A, so this one was A. So how this problem got worked was in the given table, so fill in the given table for the following shaft and hole limit. So this one's all been filled out. Let's just back step through how this was filled out. So really, some of it's already given. So A, we're looking at problem column A here. It's got a shaft and it's got some limits here, or the shaft limits. Maybe this should be one word, shaft limits. We're saying the shaft limits are 0.9975 to 0.9963. And so really for the limits row here, we just went to the shaft column because the blank ones will just say that about the same, right? If I go down here where you're going to be filling them out, it's just they still got the hole and shaft columns here. We just got to fill in this data. So what they did was back up to the top. I went to my shaft and I just essentially applied those dimensions. So it's actually 9975, 9963. So these are kind of my limits of the shaft. The limits of the hole are just what's right here in the chart. 1.002 and to 1, okay? Whether you put these in either order maybe doesn't matter. Maybe eventually it might matter. There is definitely, when I stack dimensions like this in my dimension style, it kind of matters maybe which one's on top and which one's on bottom, or which one's on the left or which one's on the right. So we'll talk about that later when we're actually applying dimensions on our drawings. But for right now, I've just pulled this information right off the chart. Then the basic size, this is something you just might have to recognize. So if I just talk through this, how a basic size of this was chosen, these are all bases. This is a relationship based off 1 as the basic size or the nominal size. I think what I found is maybe the bottom row of these is probably your closest basic size call out here. So A is a basic size of 1. We're working around the dimension of 1. One might be what's called out on our print, but it might not be sufficient for the fit. So we might have to tolerance it. In this case, it's probably 4 3/4 is the basic or nominal size. If it was C that we were working, it's a 1/2 inch kind of basic or nominal size. This is a 5 inch basic or nominal size. This is an 1 1/4 basic. So I'm using the bottom row as my basic or nominal size here, which maybe wouldn't be widely understood, but maybe you could take a guess at that. When you look at if you looked at all four of these dimensions together, you'd say, well, which one are they probably all based around? That's a 1 inch fit. So it goes back to my example where I showed that AutoCAD document of it's actually almost exactly this document of 1 inch and 1 inch. This might be the basic size. Well, this is not going to fit. 0% of parts fit. So let's apply this tolerance that's in this list here, maybe. So back to my worksheet. So it's a basic size of 1. What is the tolerance there? Well, what I want to know is the difference between the two. So all we've done is a subtraction problem for on the hole, not between the shaft and the hole, but just between the hole's allowed size. If we minus 1 2/2000 from 1, we ended up with a tolerance of 2,000. So essentially, my part can vary on the hole from 1 to 1 2/2000. So really, I have a tolerance of 2,000. Could be somewhere in between there. It could be 1,000 and still be within tolerance. If it was 3,000, I'm out of tolerance. Like if something is actually size, when I measure an actual size as an inspector, maybe if my part was supposed to be this tolerance of 2,000 and I measure that it's 3,000, I'm out of tolerance. Part rejected. So it's going to be too big of a hole potentially. All right, or too small of a hole. If it was under 1 inch for the hole, it's out of tolerance. So potentially here. And then shaft. So we've done the subtraction on the shaft as well. So 0.9975 minus 0.9963, we end up with 12 thousandths. 12 thousandths? That doesn't sound right to me. We end up with 1.2 thousandths. That's how that would read out in that chart. 1.2 thousandths right here. Yeah, it would be 12 thousandths if the 1 and 2 were over the other way left. So 1.2 thousandths. So then we need to talk about MMC and LMC. And so let's look, and they're just kind of inverses of each other, and that's why this hole and shaft relationship is great for this. The MMC, that's maximum material condition and least material condition. So yeah, maximum material condition and least material condition. And that's definitely found in that they have some definitions of that found in that textbook PDF for sure, where I was pointing out earlier. But this is where we're going to talk about it just a little bit more. So MMC, maximum material condition. It's the size where the part consists of the most material. So if and then they've explicitly they're actually looking at our exact A column problem here. And so they're calling out the largest most material. So let me just think about that for a minute, and maybe I'll pull up my CAD document because it's really important, and it's going to be important in next semester as well. So if I zoom in here and I look at a shaft, so a maximum material condition on the shaft itself will be when the shaft is the largest size, when it has the most material. So if I was looking at the whole, if I was looking at the shaft column, sorry, and I think of the maximum material condition, it just makes sense to me that it's like when it has the most material. And so it's going to be a larger diameter, the largest diameter, of those tolerance dimensions, the larger one is going to be when the shaft is at its maximum material condition. It's like the largest size it can get. And then just converse to that uh, is the least material condition is when the shaft is at its smallest, like allowed size. And of course, our tolerance is the size in between those two, of how much that can vary from least material condition to maximum material condition. So in a shaft, it's like the most material, the largest diameter, to the least material condition or the smallest diameter. I think that makes pretty good sense, right? It's just the opposite when we look at a hole, though, just so you know. Now let's look at the hole, and we think about the most material condition. So if this hole has the most material that it can be, if I have a tolerance that it's allowed to vary from 1, It's actually going to be the smallest hole size because that's actually the material is like into the hole more, and that's its maximum material condition, which makes a smallest hole. And if it's the least material condition, means my hole had like all the material that could be removed has been removed, and now it's actually the largest hole. It has the least material in it. Does that make sense? That's really important. If that doesn't make sense, I don't know. Watch this video and play it back over and over and over again. But so they're just the inverse of each other. So and this, yeah, that's just something that I want to point out. And this LMC and MMC is the shorthand notation for that, and it's going to haunt our life for the next till May. The least material condition on a hole is going to be when the hole is largest. Yep, because the material has been removed. It's kind of how I visualize that in my brain. Yeah. And then I know it's the most material condition because it's the smallest hole and it's like got the most amount of material in it. And if I can remember one, I usually remember the shaft, and then I just remember that the hole is opposite. So to me, that's why I start with the shaft, because it makes most sense. The maximum size of the shaft is when it's largest, it's the biggest, and the least is when it's the smallest. And then I just always remember the hole is going to be opposite of that concept. And that's how they're going to work together too, by the way. I mean, they kind of are like inverses of each other, and that's how they work together. Yeah, yeah. Okay. That's important. Super important. Probably the most important thing I said all day. So I should just stop saying. No, let's keep going. That is important though. That's what's going on here. So when I look at this and they ask me, well, what is the MMC of the hole? Well, that's going to be the maximum material condition of the hole, which means it's going to have it's the smallest hole size. Maybe it's easier to start with the shaft column, but I'll stick with what I'm saying. That's how they came out with the maximum material condition is one. It's the smallest hole. And the least material condition of the hole, when the most material is removed, it's 1 and 2 thousandths. Makes sense, yeah. And this one over here is a shaft, which maybe is easier. The maximum material condition of the shaft, its largest diameter. So of those two numbers, this is the maximum material condition. And this is the least material condition. So I'm just filling out those. And then we have, obviously, I probably should have shoved this over to the center, but it doesn't really matter where this is. I've got some that are not center. It doesn't matter if these end up being pushed over, it really doesn't matter if they're center justified or not. This is just a thing. But so the max clearance, let's see how we came up with that. I'm gonna scroll down to this like little explanation here. Max clearance. The maximum clearance is the maximum amount of space that can exist between the hole and shaft. The maximum amount of space that can exist. So clearance may be positive, a space, or negative, no space. So let's just stick with the first sentence. It's the maximum clearance is the maximum amount of space that can exist between the hole and the shaft. So the maximum amount of space is going to be the LMC of the hole minus the LMC of the shaft. And I should end up with this. So I'll pull up my calculator here. But it's the LMC of the hole minus the LMC, because if we think of the hole is the biggest hole, so it's the sloppiest hole as I kind of think about that. It's just like this big wallowed out hole, as big as it can get. And then the shaft is going to be as small as I would allow it to get. So we have this like maximum clearance. This is kind of how loosely the parts can fit together, or potentially, and that's what it said. It could be negative or it could be positive because we do sometimes want fits that are forced together, and we use that real specific tolerance relationship to force them together. In this case, if we do the math, which would be I'll pull up my calc here, right? I should end up with this 0.57, but it's the least material condition of the hole. That's a 1.002 minus the least material condition of the shaft, 0.9975. Oh, wait, 63. Yeah. I should end up with a 0.057. So that's like if I had those two and they were with, they were inspected to be both in their least material condition form. This is kind of how loose that it would be 5.7 thousandths of a fit. So it would be a clearance fit. It's a positive number. So that means that we have like clearance between the two parts, which I guess it's saying it's a max clearance. So the minimum clearance is going to be just the opposite relationship. It's going to be when my hole size is its smallest because there's the most material condition in there, and when my shaft has its largest diameter. So this is going to be like, oh, everything's been made and it's on the big size of everything, or kind of, I guess, yeah, big size of shaft, and and the most material in that hole. So I do the difference of that. So I take the maximum material condition. I'm going to subtract these two from each other now. And I think there's probably, does it show that? Yeah, there's the MMC, the LMC, max clearance. I think there's a minimum clearance here. So this is all I'm doing is the minimum. Oh, wait, the maximum clearance is the minimum amount. Oh, that word should be changed, I feel like, but that's the minimum clearance is the minimum amount. Yes, this word is wrong, by the way. Like I can fix mine, but it won't be able to fix yours. This should say minimum. Sometimes I don't read these like proofread them super carefully, but until I'm doing this and I'm like, oh, that should say minimum here, but save it because we're talking about a minimum clearance. So it's the MMC and the MMC subtracted from each other. So let's go back up. I'll pull up my calculator here and my sheet actually right here. Here's my calculator. We're looking at MMC. So just make sure you subtract them correctly, or you might end up with a negative number thinking that you've got a force fit and you actually have a clearance fit. So take a look at the numbers before you just subtract them from each other and make sure that we're looking at this as like, okay, it's going to be the MMC of the hole minus the MMC of the shaft. So it's going to be, if I clear this out, 1 minus that 0.9975. And you might be able to see some of these off your head. You don't have to do a calculator, but that's fine. That's 2.5 thousandths of an inch is what if the parts were at their maximum material condition, smallest, that's kind of the smallest diameter hole and the largest diameter shaft. We've only got 2.5 clearance or 2.5 thousandths of clearance. So that should be okay. We're at our part size, so yeah. And then the type of fit, we just say, this is just something I'll be like, well, what's the type of fit? Well, this is a clearance fit, but how would you know this? I think there's a little chart here at the bottom right here. So here's how here in this particular chart, this is maybe this is universal knowledge for different kinds of fits, but so a clearance fit is when the minimum clearance is greater than 0. So what was my minimum clearance? Minimum clearance. So this is greater than 0. So I have a clearance fit. I always, no matter what my part size is, there's always going to be clearance as long as my part's within the tolerance, essentially. As long as I'm restricting my part sizes like this, I will always have a positive value here, and that's a clearance fit. It's greater than 0. So let me see what else could happen here. So some of these problems you might work fall into different categories here. I could have an interference fit if my maximum clearance is less than or equal to 0. So I would have an interference fit. And how I'm evaluating that is really from these min and max relationships here. And then what else do I have? A transition fit. That's when my minimum clearance is less than 0 and my maximum clearance is greater than 0. And then would have a line fit if my minimum clearance was 0 and my maximum clearance was greater than 0. So not that I need to understand exactly how that means these parts are working together, but if I can identify the clearance that I have and maybe categorize it here, it'll tell me what kind of a fit I'm looking at, which might be real critical for some real critical applications. All right. So that's how we would do. What's that? Yeah, it's really not. Like some parts are designed to have interference like that. Yeah.
It's not. If it is a problem.
If it's not designed, it is a problem.
It's
Yeah,
a
yeah.
metal shaft through a nylon. You're
Yeah. Yeah, yeah.
the heat up.
Exactly what I was just going to say. Like in my experience, we made a lot of big, huge augers, big screws. Because in food processing, they use a lot of screw conveyors. It's a great way to transfer stuff from one point to a next through a closed auger system. And so, and even like huge augers. Anyway, what I'm saying is when we build our augers, and we build some huge, like 10-foot diameter augers, sometimes 8-foot diameter augers to cook potatoes. Essentially, they put them in a big hot bath, and then the screw actually pushes the product through, and then it exits and it cooks the product just right in a huge, yeah, they call it a blanchard. And it's just a big screw. But so our manufacturer, I mean, our technicians would build these things. And to build the auger's shaft, so an auger is like this shaft assembly, and then it has flights around it that look like a screw, right? I think we've all can visualize what an auger looks like, I hope. They call them screw conveyors as well. But In some cases, they would to build the shaft, they would I'm not going to be able to like word this out and visualize it. I should like pull up a YouTube and yeah, it's kind of like that, right? Yeah, it does have some auger flights on the on the center spindle if you still have one of those. Mine doesn't have a spindle in there anymore. It just kind of like yeah. Yeah. But yeah, kind of similar to that. And but there was cases when we build ours that they'd have to buy they'd cut these big chunks of plate. They would heat them up really hot and they would insert them on the shaft while they were hot and expanded. And then as they contracted, there would be an interference fit. So they can use heat to make an interference fit actually slide together. And or they can cool something and chill it down really cold and shrink a material property way down and then slip something over it that's maybe been heated up. And so you actually create the clearance you would need to make the parts fit together. And then as they go back to their room temperature, they kind of have an interference fit. They're locked in together. And so yeah, things can be designed to look like they will be not able to fit together, but with some heating and cooling properties, we can actually make force the fit together. Yeah, super cool. Super cool. I love that stuff, man. Yeah. When they were heating up those big. Anyway, I'll have to. I'll look for this in the next day or two. Look for maybe somebody like building an auger and using kind of force shrink fit concept. So I can put some to what I'm saying. I'd like to show some imagery of it because it's hard to visualize. But I mean, I can visualize it perfectly because I've walked past it and seen it over and over again. But so B, yeah, like I can maybe kind of run through B, but it would essentially be like the limits here for the whole, or actually, or what are just given in the column here. So the limits for the whole here would be, and it really wouldn't matter which order you maybe put these in, potentially is what I'm saying. It's like a 4.751. And I'm really not going to put two or anything. I'm just going to like space myself over and write the other dimension. It's 4.750. And maybe I'll just hold that same decimal place so they show me. So that's like the whole limit there. And then I've got the shaft limits to look at for this particular B problem here, right? My shaft limits are 4.7494. And I'll just space that over. It doesn't really matter. 4.794 to 4.7487. Okay, that looks like the two numbers that I'm associated with. What's the basic size? It's usually in the last column, or it's something I should maybe just the nominal size is usually just like a nice, easy to look at dimension. They're usually not these odd, weird dimensions. So it's this 4.75 is actually my nominal or basic size for this particular shaft and hole combination. It's pretty large. Like a 4-inch shaft fairly is large. I mean, that's a pretty big chunk of material there. I don't remember what the size one of the one we just did. What was it? Fairly small. That's pretty small shaft, but it does pretty good duty. Once we're up to a 4-inch application, this is large. I mean, this is like mining. I mean, this could be food processing type work too, but it's definitely large shaft. If you're up in this 9-inch range, that's a large shaft. I mean, we're talking mining equipment potentially. I don't know. That's big. That's a lot of material. So yeah, it's kind of yeah. It's yeah, it would not if it's not clear to you why I picked that, that's okay because this is a little bit confusing and they don't really explicitly say which one is the basic size. So it is the bottom row of these, which are kind of the most friendly dimensions of the columns, you know what I mean? Like it's this bottom one that is kind of the whole, it's kind of based off the whole, but it's yeah, these are kind of the basic sizes for sure. I'll look at the other ones on the other worksheets and make sure that stays consistent, but the other worksheets are a little bit different, but the tolerance is going to be the difference between these two dimensions. So I'm just going to subtract them from each other. And some of this you might be able to do in your head, but where you can't, just pull up your calculator or whatever and just punch in the numbers. So I'm probably going to do it to make sure that I get kind of a positive value here. It's going to be 4.751 subtracted 4.75. And this is going to be the tolerance. It's kind of the allowed variation of my part from big to small is only 1/1000th. So really, this is a pretty tight tolerance on a large shaft, actually. So 0.001 is what I have for the tolerance on the hole. Sorry, on the hole, and then the tolerance on this one is just going to be the difference of these two here. So yeah, back to my calculator here, right? 4.7494, 4.7494 subtracted from 4.7487, 4.7487. I end up with 0.7 thousandths essentially of allowed variation. So 0.0007. Very, yeah, 0.0007, yes. Which I'm just calling that 0.7 thousandths because that'll help you like when we go to that chart, understand it maybe a little bit better. But yeah, it's like machinists and the way they talk and some like the charts are simplified because this um and we don't need them on this here, but when I get to them, the reason why the charts are in shorthand notation is just because they carry a bunch of zeros, and it makes my chart and the column width have to be way bigger. Because what I'm talking about is this. When you go to start using these, that's why they've simplified what a thousandths look like here, is because they would just be carrying a bunch of zeros on this chart that just make my columns wider, and so they've condensed the chart to be a simplified version, which really confuses people. But it's because they're showing them in thousandths of an inch, but kind of like some of them are fractions of a thousandths. So essentially, if I looked at the dimension I just figured here, it would look like point. Let me see what my dimension was, by the way. What was it on my calculator? Sorry, I never wrote it down here. 0.0007. Yeah, so I'm going to put this in here real quick. 0.0007. That would look like point 0.7 on these particular charts. That dimension would show up as a 0.7, means zero point 0.7 of a, yeah, no, of a thousandth. Oh, it's confusing, but it's just to simplify their chart is why they've made it this way. And machinists and other fabricators are used to looking at thousandths of an inch in this form. We might not be. It might be totally confusing to us, but the more we use it, we would get familiar with that notation and recognize that, oh, we just don't need to display so many zeros. So the MMC is going to be the difference. If you just can't remember, always scroll up to that for the MMC, right? Just kind of look right here. The size where the part consists of the most material. So the largest number of the shaft and the smallest number. Where it consists of the most material. So if I'm looking at the hole, the most material is going to be the smallest hole size. So it's going to be that 4.75. And the most material condition of the shaft is going to be when it's at its largest diameter. So which one is the larger one? 4.7494. Yeah. And then the least is going to be just the opposite. It's going to be the least material condition for the hole will be when it's at its largest size. The most material has been like removed. So 4.751 would be its LMC. And then this one is going to be the smallest diameter of the shaft, or a 4.7487. Yeah. The reason why somebody like a drafter might use this is I might use some charting like this, and I might build like I might build my own little spreadsheet so that I could like know how to go build my dimension style in on my drawing. Like this might help me to like build a spreadsheet or something and put together and be like, okay, what I need to know is like the tolerance from plus or minus. And so a charting like this or figuring out some of these dimensions might help you build a dimension style in the future. And so I would maybe use something like this. Of course, you could do this on paper too, but a lot of times if I was going like I might have an Excel spreadsheet where I was building where I'd be recognizing which kind of tolerances I'm using on my drawings, and maybe this would help me like build a dimension style a little bit quicker. So, and maximum clearance. Yes, exactly right, right? The maximum material condition is going to be the smallest hole. There's the most material in the hole, and this is the biggest diameter shaft. Mm-hmm. Least material of the condition of the hole means I've removed more material, so it's at its largest size, and this one is my smallest diameter. Yeah, and then my max clearance is going to be, just like it says up here, the maximum clearance is the maximum amount of space that can exist between the hole and shaft. So it's the LMC of the hole and the LMC of the shaft. and the difference between the two. Maybe that shows it as a problem here, like the hole minus the shaft here. So let's take a look on the LMC. So the hole minus the shaft is going to be my max clearance. So I'll pull out my calculator, right? 4.751 minus 4.7487. 0023, so 2.3 thousandths of an inch. My min clearance is just going to be the opposite value. So it's going to be when the hole is its smallest and when the shaft is its largest is my minimum clearance that I have. So what is it? It's not. It's like if in inches we would drop it actually. So it's okay if you do put it though. I'm not being critical on like if it's dimension right like to ASME standard, but technically the ASME standard would be inches or yeah, there might be some test questions where they say, is this, yeah, because if it has the zero in front of it, I should infer that on a print, that means it's a metric dimension. If I'm carrying the leading zero. Yeah, that's confusing, but that is one identifier on a sheet by ASME standards. In order to choose that, though, I'd have to say, is the company even following those standards? Because I would want to make sure that they were that they just didn't do that out of habits and they didn't realize that they were actually implying that's a metric or standard dimension. So you'd have to make sure that if you see that, ask yourself, is the company even following standards before I would say, because that could be the case they're not, and they haven't even realized that they're implying a standard that doesn't exist or they're not following. So my minimum clearance here though is largest and largest, right? So I just need to go or smallest and largest. So the hole when it's at its smallest or the most material in it, right? So 4.75. Yeah, clear this out. And subtract it from when this is at its largest size here. So the largest size of the shaft is the right here, 4.7494. I don't know if you got that it's 0.6 thousandths of an inch on its minimums. So pretty tight tolerance here, 0.0006. That's not a lot of room when it's at its when everything is size as taking in its most material condition form. But there is still clearance, right? So then I look at this and I say, well, now categorize it here. I'm a positive value, so let me just at least know that, and say when I'm looking at the type of fit from this little chart here, as long as my minimum clearance is greater than zero, I'm a clearance fit. I'm not less than or equal to zero for an interference. My minimum clearance is not less than zero, so I'm not even a transition fit and my minimum clearance doesn't equal zero. So really, just based off my minimum clearance, I'm only categorized as a clearance fit here in this particular one. That's how I would analyze that, and then I would write that in here. This is a clearance fit. Clearance or clearance? What is it? ANC, clearance. Okay. Yeah, seems like I pronounce it more with an E here, but so I'm going to confuse myself. Clarence, Clarence, turn up. Yeah, exactly. Are we talking about a person or clearance? Both. Clarence, come on. So then I would be saving this. And so you're going to continue to just do C and D by your lonesomes. I'm going to move to the next worksheet. So you can save what you've done here, whatever. Let's look at the next worksheet. I told you it's a little bit dry, but it's important stuff. And doesn't mean you have to understand it perfectly, but it's just exposure to this concept of a little bit of research and maybe some recognition of where I might apply this on my drawing, controlling some part size because I can't control perfect form. So I've got to allow some variation. Okay, so what's number two? I got worksheet number two. I just need to pull it up. Worksheet number two should look like this if you download it. Looks pretty much the same, so they're really easy to confuse each other. They're all kind of built the same. I think the what I'm highlighting here is the problem that it's actually worked in the example here. So this is tolerance number 2. It's kind of the same thing. We're going to find the limits of the shaft and hole for the following basic size fit combination. So this one different than the last list. It gives us a basic size. These are still all individual problems. I think when it's so we're going to look at the example as the orange highlighted problem worked on. I think when it comes down to this, I re-show that here because this is where you're actually working on these problems. Looks like we're going to do quite a few of these. We're going to complete the fits for 2, 3, and 4 for basic size quarter inch here because we're going to do number 1 together up above. And then we got to finish 2, 3, and 4 for basic size quarter inch. And we got to complete fits 1 through 4 for basic size half inch. So we're going to essentially, the other ones you're going to do are the orange highlighted ones here. So let's go up and look at this one. So it's a little bit different, but it's got the same idea. It's got the problem, it's got an example, and it's got some explanations about how we found the specific row information. So let's take a look at this one. So this definitely is going to refer to that to appendix, I think, for sure. So we're looking at a basic size of a quarter inch. So that's my first thing that I need to know. I'm basing everything off of a quarter inch. We're in inches again. Here I'm keeping the leading zero. So that was a good question. Whoever wrote this is an idiot. No, not really. But this I should have left that off, but it's all right. See, even I cross, even I, standards is as standards does. Come on. Yes. Quarter inch essentially. And then it was called out for us to do fit 1, which fit 1 is a RC3 fit. An RC3 fit. So I'm going to go, this is going to be my code book. This is going to be my code I'm looking for in my appendix. I'm looking for in the inch, I'm in inches, so I'm looking for in the inch charts, looking for an RC3 type fit. That's kind of all you're given here to actually then figure everything else out from, are those 2 values here. I got to know hole and shaft nominal or basic size, and I got to know what kind of fit we're trying to fit here. And doesn't mean I know what the heck this even means at all, but I think it's a running clearance fit, maybe. Clearance fit. Yep. We'll see if that's what it is. And then we from the chart, we were able to determine these values here. So I don't think I'm pulling these off of I don't think I'm doing any math here. Maybe the limits I'm doing some math, but so let's it says we're going to find it in that table, but it's going to be found in the appendix is where I should say, I guess. The definitions for these kinds of fits are in that textbook. But really what I need to know is I need to go to that appendix. I wish that said that in my fit class here or something. Or maybe it says here. I don't know. It should point me back to that appendix is what it should do. Yeah, A1 through, this is the appendix, A1 through A7. I wish this just said appendix. But that's where we're going to find our values. So let's go look. And maybe I'll pull that up. Maybe I'll split my screen here so I can see that there's my worksheet I'm working on. Maybe I'll zoom in a little bit here. And I need my appendix up, which I have right here. So I'm looking for an RC3 type fit by Engineered Design. So actually the first page is RC fits. That's good. RC 1, 2, 3. So I'm really dealing with this column right here. These are the RC3 class of fits. And I think on this document, that's the only place you'd find them. If you kept scrolling through all this stuff, it's only on the first page, the RC fits. There are some metric ones coming down in here, so just be careful that you don't use a metric chart for your inch class of fit. So I'm going to go up to the very first page, actually. It has the RC3 fit right here. And then in order to know which row, I have to know which is my nominal or my basic size that I'm looking at. And so what I'm looking at here is, this is a quarter inch, 0.25 hole and shaft basic size. So I come over to this far nominal size column furthest to the left. And I'm looking for that dimension to be, these are usually plus or minus. So they're gonna like, you're gonna hold some tolerance up to, some shaft and hole size, maybe not including. And so what they've got is like an over and 2. And so this would be 0 and up to 0.12. But nothing, if it's 0.125, I'm over that. And so I'd come into this category here. This would be 0.12 up to 0.24. This is still not our row because we need to go up to 0.25. And so this is only from 0.24 down to 0.12 of my shaft and hole size. So I got to go to the next row here. This is 0.24 up to 0.4. So my dimension, my basic dimension fits in this row right here. Essentially, they've got like these tolerances will apply to multiple shaft and hole relationships as long as they're within this, there's kind of within this sizing here. So engineers have determined that we can apply these tolerances if our shaft and hole fall within these sizing constraints here. If they fall outside of these, either under or over, then I need to go to the next row and decide where my shaft and hole fits in here. And then the tolerances are going to change associated with that. So yeah, it's just that the way the engineer would have designed this is that we're kind of instead of having like a instead of having a tolerance for every single size of shaft and hole combination, we're able to kind of give us a range of shaft and hole sizes, and then we know these tolerances across this will work for these kind of class of fits. So this is kind of confusing, but it's like they've simplified this in knowing that these tolerances will work with this range on the leftmost column of size of hole and shaft. Yeah. Yeah, if is I just have to really watch my basic size and know that it fits within the range that's given here. If my basic size doesn't fit within this range, I need to either look above it or below it and to see. Yeah, it's got to fit in between here. It can be right on that for it just can't be, yeah. Anyway. Yeah. I'm just saying this is a range here. Maybe this is confusing to look at, but this is a range of sizes is what I'm looking at here. A range. I think that's good. 0.25 fits here is what I've determined actually. It's on the one, two, third row down. 0.25 is actually in between these two values. This isn't a negative value. This is a between. I would read this minus sign as a between. For shaft and holes between 0.24 and zero point 0.4. Mine's 0.25, so it fits in between this range. And I'm an RC3 class of fit, so I'm going to go over to that column, which is this. Here's my numbers that I'm dealing with, and I could probably almost like highlight that or something, right? Like where I'm going to look at for my values, probably going to pull them right out of here, is going to be this one, right? RC, yep, right here. These are my values for my particular example problem to work with here. So I'm just going to see what information is. I remember these are in thousandths of an inch. Okay. So I'm going to come over here and I'm going to say my table value for my hole. And I feel like I could put either one in either. I'm not explicitly saying which one goes where here. It's just that I'm looking for my hole values that's allowed. And here I've got hole and shaft. So my hole values are a positive zero point 0.6 thousandths, which is written like this, 0.0006. That's like a zero point 0.6. So this is the way I might write it over here. This is the way I would see it in a chart that's simplified. 0.6 thousandths. And it can go to zero. I can't be any over, or I shouldn't say I can't be any under that, I guess. So how I interpret this is if I'm looking at a hole, this basic size with this class of fit, I'm restricted in that I can't be over that size at all, or I can't be under that size at all, I guess is what I'd say. I have to at least be this size, 0.25, but I could be maybe this much oversized, 0.6 thousandths over that. So my whole size, so there's going to be like a limit here, or there's going to be a tolerance that I'm allowed here. It's only that. So I know that's a little bit confusing, but it's probably how I'm saying it. Let me interpret what the shaft values are allowed to variation. Because what I'm looking at is how much they can vary, what the tolerance is. So the shaft one is going to be kind of a negative half a thousandth, 0.5 thousandths. So that's the first one I put in this column here. Negative 0.0005 is the same number as this right here. They totally shortened it. Yeah. Otherwise, you'd have these stupid columns that would be really wide with all these zeros that really are just redundant, kind of. Yeah. This is definitely shorthand notation for, think of somebody that uses this a lot, they would recognize this pretty easily of what that is. Yes. For us, it looks really foreign and it confuses the heck out of us. So don't think that that's zero point 0.5 of an inch of tolerance because that would not make sense. Like if I thought logically, my shaft size is only a quarter of an inch, so there'd be no way that I should allow something to vary double its or I would I'd be like negative 0.25 if my shaft would be invisible in the negative land. Anyway, it's the more I talk about it, probably the more confusing I'll make it. So then the other dimension I have for its limits are negative 0.0009. That would be like zero point 0.9 thousandths, according to this. So that's where I've pulled this data from. And now the limits, and I think that's going to tell us that here. These table values are pulled from that. Oh, I thought it might show us that where the limits are. I thought it might have an explanation of where my limits were figured out here. That's kind of funny, huh? Yeah, I think that you'll find that
Yeah.
I think it's because they want to hold the place. Yeah. I think it adds clarity to their table for sure. Yeah. And remember, they're not like dimensions on a print either, so it's like a chart. Oh, don't worry about stuff. It's too far in the future. I was just going to see if it shows us where, like, to find your limits. I understand that we've added the upper limit to the basic size. That's how this was found. I just don't know if that's like shown here. Um, Fit class, we get that we're finding that. Table value, find your fit you're looking for at the top of the art. So this is RC3, then find the basic size on the left hand. Oh, yes, okay. So I've explained that. Add the standard limits to the whole. Oh, yeah. So I guess to find what I don't on the first worksheet, they actually broke down. I actually have each one separated. Really, the next thing we're doing is for the limits is right here. Add the standard limits to the hole and then the shaft. So we're adding the limits. So the hole and the limit we're adding together. It's reminding you that the chart is in thousandths of an inch. So we end up with this as the least material condition of the at the upper limit. This might be confusing too, but all they essentially all that we've done is we've added that upper limit to our basic size, and so the whole in its least material condition form would be up to being able to be this big. Basic size with a tolerance applied, I can actually get my hole up to being this big and still be within this particular for an RC class of fit, I'm allowed to be this big of a hole in its least material condition state. And then at its like maximum material condition, when it's at the smallest hole size, I'm not allowed to vary anything off the basic size. So I've got to at least maintain a hole that's 0.25, can be as big as 0.2506, and anywhere in between. Generally, I can be anywhere in between here as long, and then I will classify my holes in RC3 or an RC3 class of fit here. So my hole can only be between these two sizes. So that might look like on a dimension, if I was dimensioning that on a drawing, that might look like I would call out like I would have like modeled my part to probably be 0.25 so that when I dimensioned it, there's my basic size showing up, 0.25. And then I would have built a dimension style that says uh, plus 0.0006 minus 0 would be what my dimension style might look like. It would be that 0.25 is the given dimension, and I would have modeled my part that way, drawn my drawing that way, and then I would have that tolerance allowance applied to the other side of the dimension, kind of in a plus or minus form is one way to display that. So not that we're going there, but I just want to say like why I would build a chart like this as a drafter, and maybe this would help me build a dimension style right there. That would be an RC, and then I would probably call my dimension style RC3 class of fit or something like that. And then I would make my no, I'm not I'm gonna go off. And then if I was a true engineer, I would like make it so that my spreadsheet, I could just apply this value to my spreadsheet and these would automatically apply. Like I could build a calculating spreadsheet to where all I have to do is punch in this shaft number, and I've already built my spreadsheet to apply these tolerances to where it spits me out these dimensions. Yeah, that's how an engineer would think. They build themselves a spreadsheet that they could just input like minimum variables to output the tolerances. This is getting into the weeds a little bit, but that's how a lot of engineers uh, fast track their work a little bit. Yeah. All right. Build a calculated spreadsheet, which we should do more in math, really. You do a little bit in architecture. I think she teaches one class of kind of spreadsheet type math, maybe for cost estimating, which is good, but we can use it as a mechanical application. We can use Excel as our calculator and then share that spreadsheet with other people. Speed up workflow. Okay, back to what we're doing. The other thing, so on the shaft, we're doing the same thing here. It's saying that my shaft size, I'm going to apply this value, this net, I'm going to minus this from this value here. And so and I should be looking at yeah. So I'm taking my 0.25, subtracting 0.5 thousandths, and I end up with this dimension of my shaft in its maximum material condition. This is I wish I would have labeled that maybe, but it's okay because they kind of talk about it down here. That on the shaft, it's showing it as a plus or minus. I can think of it as subtracting from that to get my maximum material upper limit for the shaft. It's going to be the biggest my shaft can be according to my tolerance, and the biggest my shaft can be. It's always got to be undersized by a half of a thousandth or 0.5 thousandths. It never wants us to be anywhere near the basic size. We have to always maintain a smaller size for this particular class of fit. So that's why I subtract this value. And it's nice that it's a negative value. It shows me that I need to subtract it from this. And I get this value here. And that's its maximum material condition. And then I've got to evaluate it for its least material condition. So I'm actually subtracting a little bit more, zero point 0.9 of a thousandths here, according to my chart. Yep. And I end up with this least material condition of shaft right here. So now I have my shaft can vary between these two dimensions, but it can't be any bigger than this, and it can't be any smaller than this. Otherwise, I'm going to have not the right fit here. So this is definitely a clearance fit. I'm never going to have, not that we need to analyze that, but that's all the information we're filling out on these charts. Is really referencing this and then trying to subtract or add those values to the basic value to kind of build uh, the limits of the dimension of what the limits of the feature, I guess, the hole and shaft. So let's do one together then from scratch, and then we'll call this day pretty much the driest day on record. But there's a lot of work here for you guys, no doubt. But I think we can do one here. So let's look. Let's look. Ron. Hey, let's see here. We need to size fit too. So we gotta finish all the orange ones here. So I'm still looking at a 1/4 inch basic size. So that's what's gonna go in here. Is 0.25. Whether you put the zero or not, I don't care. 0.25. That is the basic size that we're looking at for A, and then Ron. And then the fit two, we're gonna need to look at an LC2 type of fit. So we're gonna go to our charts and look for a locational clearance fit number two, LC2. And then we're going to pull out those values that it gives us in the chart here. So we're going to apply the table values here. You can move these around a little bit too if they're kind of, not that they're perfect, doesn't really matter. But we've got two values for the hole that we should be looking at. And what we're looking at is kind of tolerances is what we're pulling up as values. I kind of wish that said like the tolerance maybe or something. LC2. So I'm back in my appendix here looking for an LC2 locational clearance maybe. RC, there's 2 pages of RC fits. What's the next page down? LC, locational clearance fits. LC2. So I'm going to be looking in this column based off my shaft size, whatever my nominal or basic size is. So I got my highlighter ready. I'm looking for 1/4 inch. It's probably going to be about on the same row. I think they're about the same rows. Here's my 1/4 inch. It fits on row 3 of this particular chart. 0.24 to 0.4. I'm in here as a 0.25 fit. I'm looking for an LC2 class of fit. Yep, this one right here. So I'm looking at these values right there. Not I'm kind of outside of the lines, but I color outside the lines. These values here. So I'm looking at the hole. It has a positive. It looks like it's 0.6 thousandths again. So I'm going to come over here to my hole, and maybe I'll put this one over here. Doesn't matter which order you put them in, just you got to kind of keep track of which ones. So that's my chart says plus 0.6. So that is actually a 0.0006. That's how I would recognize that. It's like 0.6 thousandths. Yeah, and then it can vary down to 0. It doesn't want me to be on my hole. It doesn't want me to be anything smaller than the basic size. So I say 0. My hole can never be smaller than the basic size, but it can be bigger by this much for this particular class of fit. So I can figure that out right now before I even look. Let's look at that and say all this is how big my hole can get. So this is going to be least material condition of a hole because it's its largest size. 0.25 plus that, I can probably see that in my head is 0.2506. If I add those two together, and then if I add 0 to that, it's still 0.25. So there's there's my kind of my limits. My hole can be 0.25 and up to 0.2506. Let's look at shaft and its table values. So the shaft for this particular fit, for its maximum material condition, I guess is what I'm looking at here. It's going to be the largest diameter. It's only 0. So the first number I have is 0. So I'm not allowing my shaft to be any bigger than 0.25, but it can be up to 0.25. So it can be the basic size. And then for its kind of its least material condition, I'm going to subtract zero point 0.4 thousandths off of that. So that looks like 0.0004. And I should put a negative in front of it because it's a negative value. That means my shaft can vary 0.25, and then I could subtract zero point 0.4 thousandths from that and come up with the number here that it can be. And that's what I need to do. So essentially, if I subtract 0 from 0.25, my shaft maximum material condition stays at 0.25. And then here I need to subtract the 0.4 thousandths from 0.25. So in the event that you need a calculator, just use it. 0.25 minus 0.0004. This is how small my shaft can get, 0.2496. And it's because it's a positive value. Look, like your chart is kind of helping you steer that way because they're showing that this is going to be subtracted, this is going to be added. Yes. So what? Yeah, that's a good observation you make. That my hole can be bigger, my shaft can be smaller. But what we also have going on here is that my hole can also be like the basic size, and my shaft can be the basic size. So technically, I'm going to have potentially, if they're in the right, if this is in its like maximum material condition and this is in its least material condition, we're going to have a size on size fit, which may be so it's which might work. I mean, it is a locational clearance fit. It is an engineered design, but that could be kind of a force fit application there because they are the same size. So we kind of have a size on size, but for this application, we're saying that it will work because it's an LC2 class of fit and it allows us to be that way. So yeah. It might be one that if I'm the assembler of this, I'll be like, hey, machinist, always try to get to the low side of this. Hey, laser cutter person that cuts the hole or whatever. I'm going to go to my people and be like, hey, I know that we're allowed to be there, but I have a hard time putting them together unless you make them on their least material condition, maybe. Yeah. Right here, negative zero point 0.4 thousandths or what? What about it? It is. I've taken this and subtracted. Yeah, they even show that here. They consider that you're adding a negative, you're adding a positive, kind of like the way they've explained it here is it is thinking of just adding those to it, but sometimes you're adding a negative, which is a subtraction problem. Yeah, that's a little bit confusing. This is trying to explain that. Yeah, but that is all we have to answer for this. This would allow us to build a dimension style that could capture this though. So we could definitely build a dimension style that's LC2 type fit. Here's how it would look. Yeah. So then you just have a bunch more of those to do. Enjoy, and I can help too. I think that's all the worksheet stuff we'll cover today. I have two more to get through, and I can just briefly preview them. I think they're maybe the metric ones. I was gonna open them up real quick and just take a look at what worksheet 3 is. Here's worksheet 3. I think we're back to kind of but we are in metric. I don't know if this explicitly says that. I need to add that. This is metric for sure. So one reason I know is because this is 80 and an 80-inch diameter hole. I mean that's huge. So these are in millimeters here. I wish that's I'm gonna make myself a note to add that these are in metric. So one thing that shows it is that if I see this little code, this H9, capital, small letter with a slash in between them, hopefully that triggers my mind now that that's a metric classification of like fit. And the other ones we've been working on are like an inch classification of fits, like RC, RN, FN, all these things should cue my mind into being, I think that's an inch relationship, like a customary type fit. And if I see this H and capital small with a slash between them, hopefully that's like a metric class of fit. So these are metric. Worksheet 3 and 4, I think, are both metric. The nominal sizes here are going to be the lowest row, I think. Let me back that up a little bit. Definitely on the first three columns, the bottom row is nominal size. That's basic size for sure. When I come over to here, oh, and even over to row D, I would consider these all the basic sizes, but I would consider these up here the basic sizes for E, F, G, and H. I don't think you have to answer those though. Let me scroll down and look. I think you're just doing B, C, and D, so you don't have to worry about that. But it looks like to me, I can identify that these are basic sizes for these particular rows. Basic or nominal. Yep, it's calling it basic on this, but. And really you don't even need the appendix for these, right? These are the ones like kind of like what we did with the inch ones where we're pulling data, we're subtracting the two from each other, we're coming up. I think there's going to be a way to classify these down here, maybe maybe down here. I'll go over these tomorrow. I'm not making it. On Thursday I'll probably do these an example from each of these worksheets as well. So if you want to wait on these ones, you can and finish the other ones. That's great. I was going to pull up worksheet D real quick. I'm saying it is the same concept, though. It's just in metric. And I think the other one is going to be dealing with those other code classes. So let me pull up worksheet 4. It's kind of like the worksheet 2, only in the metric form. So we've got basic sizes. These are in millimeters. These are the classifications of types of fit we can have with hole and shaft metric relationships. And we're going to probably kind of fill them out the same way we were doing those. Yeah, so I'll cover worksheet 3 and 4 on Thursday, guaranteed. About like I did today. I'll put you to sleep talking about these. And then the last thing I'll do is just preview that appendix one more time. So here's my appendix. And just so you know, yeah, we've only dealt with the first couple of pages. And then eventually when you scroll down far enough, we hit the metric. It doesn't really obvious, but we hit about a page 8 to 12 is all the metric stuff, and we will start to see those other classification codes there. What did you say? 80? That's 80 millimeter. Oh, are you looking at figuring out one of the problems? Oh yeah. Hmm. Maybe that's true. Maybe you're bringing up something. You're queuing in on a brain cell that I've developed last year. I think there might be ones that are maybe I'm lacking information, right? Right. Yeah. So are you on worksheet 3? You're on worksheet 3 or 4? Worksheet 3. Yeah, you might bring you're firing off some brain cells that I remembered now because B is an 80 nominal, right? And you're looking at to figure out the IT grade for this. And let's see here. International tolerance grade number. The IT numbers are a set of tolerances that vary according to the basic size and provide the same relative level of accuracy within a given grade. The number in the fit specification represents the IT number. The smaller number, the tighter the tolerance. So find your fit. Yeah, this one I might have to actually go refer to that table and see. I'm trying to remember. Yeah, I'm not going to sweat too much about. I'll look ahead of this because you are bringing up. I do have this. This is my old one from last year, and look. I do. That's why you're firing off brain cells. I have this like not in appendix, so it's not really solvable. On for B and for its IT grade and system hole, we do not have those values in the chart. Like they probably do exist. Our chart just is cut off or limited, you know. Like I said, like our yeah. Yeah, so I have that as my answers. Like it's not an appendix. So if you're not in an appendix, you can't solve it. I kind of forgot about that. Yeah, that's good. There's all the answers. You can just go to this video because I did video all that. There you go. There's, I will post my answers up maybe after the weekend or closer to the weekend. I don't know. I want you to struggle with that, but I'm gonna end my recording here on this, and I'll post this up so you have it as a reference. And if you need